This is ECE540 Advanced Networks with Dr. Shu. Our paper is on COPE, a software-defined approach for home wireless LAN management through an open API. Our group is myself, Stephen Seppala, and Talia Garcia. The abstract of this presentation is going through the solutions that COPE attempts to solve. These problems are dense wireless network deployments at homes such as apartment buildings, Wi-Fi enabled devices such as laptops, handheld devices, and wireless entertainment devices, clustering in densely populated wireless networks, and dense networks that share the same unlicensed spectrum. The problems that COPE needs to solve are these densely populated residential wireless LANs in which AP cooperation is non-existent. Large areas of interference that can be Wi-Fi interference or non-Wi-Fi interference, and the general lack of configuring access points. This could be insufficient and static channel assignments or basic lack of user knowledge on how to properly configure the various devices. We define these problems as the following. As far as decreasing the Wi-Fi and non-Wi-Fi interference, this can be caused by, as far as non-Wi-Fi interference goes, some appliances such as microwaves do not leave wireless signals alone and can broadcast very strongly on certain channels, which can degrade or otherwise interfere with wireless signals. For Wi-Fi interference, some APs can have high airtime usage. This can be attributed to high external traffic and low PHY rates. Inefficient and static channel assignments can be caused by a group of APs that could be using single static wireless channels, or in general, lack of configuration of these APs. Here we can see two APs that are on the same channel. AP1 is having a lot of traffic, while AP2 has a lot of airtime usage. The high traffic from AP1 causes higher airtime usage on AP2. The higher the traffic, in this graph we can see that the higher traffic rate causes a higher airtime rate by about 70%. In general, higher traffic can cause more airtime usage. The solution to these problems is COPE. COPE is Coordination Framework for Open APs. COPE is a cloud-based management service using the OpenFlow SDN. The OpenFlow software-defined networking allows determination paths of networking packets through all switches. In this graph, we can see that COPE controller hosted by an ISP or a building manager interfaces the internet to the COPE-enabled APs in any given densely populated wireless network. So what exactly is COPE? COPE is a multi-tiered flexible networking framework. It uses the open source OpenFlow SDN alongside the Floodlight controller. The Floodlight controller is an open source Apache licensed controller for OpenFlow. COPE allows collection of statistical information from connected APs and collection of network data from these APs. COPE is a cloud-based controller which allows statistical configuration based on the data that it collects. COPE can be hosted by an ISP or third party because it is a cloud-based solution. The COPE API framework consists of modified Floodlight OpenSDN framework, which consists of over 9,000 lines of custom code. These custom interfaces include an access points, controller, wireless extension to OpenFlow. All of these are implemented as Floodlight modules. Here we can see an overview of the COPE controller process. The floodlight modules are the config manager, COPE manager, stats manager. The COPE manager is the traffic controller which controls the config manager as well as the stats manager. The config manager and stats manager report directly to the COPE manager, which then processes these statistical information through learning algorithms and presents history logs and various other statistical information to an end user.
COPE APs implement 3 different modules that give a set of skills to the COPE controller. The controller uses the modules to learn about any wireless activity. Using what it learned, the controller can then configure the available APs to perform at their best. COPE uses a configuration tool named Lucy to interfere with the first module, the AP Config Manager, which performs AP level configurations. Using the open source Click framework, COPE gives the basic stat reporter and the diagnostic stat reporter the ability to gather statistics on surrounding wireless connections. The table shown in this slide shows 3 previously mentioned modules: the AP Config Manager, the basic stat reporter, and the diagnostic stat reporter. It shows their main descriptions and functions that are implemented within the modules. As before, the AP Config Manager interfaces with the Lucy configuration tool to perform AP level configurations, like the channels and the transmission power. Depending on the AP platform being used, it's possible for COPE to interface with other configuration protocols, such as netconf, which installs, manipulates, and deletes the configuration of network devices. Next, we have the basic stat reporter. This module reports the added wireless statistics to the controller. It collects information of neighboring APs like beacons and MAC addresses. It's also in charge of getting the current channel's airtime usage, information about associated clients, packet transmission, statistics per local link, and getting statistics of the current traffic. The diagnostic stat reporter gives a more detailed report about wireless statistics for diagnostic purposes. For example, this module collects information on non-Wi-Fi devices such as microwaves and cordless phones, which interferes with other Wi-Fi devices. This is done by using AirShark, a system that detects multiple non-Wi-Fi devices in real time and using only commodity Wi-Fi hardware. This module is also in charge of collecting report summaries on what package contains, such as timestamps, package length, phi rates, and retry bits. The module is also in charge of getting overhead beacon information on the same Wi-Fi channel for time synchronization. The COPE controller is implemented over the Java-based open source OpenFlow controller called Floodlight. The COPE controller consists of 3 modules: the Stat Manager, the COPE Manager, and the Config Manager. They are all implemented as modules within Floodlight. The controller uses the OpenFlow with COPE-specific protocols extensions to collect data from APs and apply configuration updates. All server modules and tasks are managed by the COPE Manager module. This module manages and configures the connected APs, but it also allows administrators to create custom policies based on their requirements. It also keeps logs about previous wireless activity for diagnostic purposes and predicts wireless usage characteristics on each AP location. The OpenFlow communication protocol has capacity to exchange switch-related statistics like the flow and the queue of an AP. OpenFlow was added to the COPE framework to exchange related wireless statistics and transmit wireless configuration updates. Next, we'll talk about how the COPE framework assigns dynamic channel configuration to its APs and how airtime is managed using the Set Airtime Access API. Research done by the author of the paper concluded that more than 50% of Wi-Fi owners had a fixed channel configuration, which lead to inefficient use of the spectrum. In the COPE framework, by collecting all data from neighbors' APs and the airtime usage on different channels, the controller can fix this problem of inefficient spectrum use and perform better channel assignments. An exercise was done to study the benefits of the COPE controller by assigning channels to different APs. 12 residential COPE APs were deployed for a length of 6 days. 2 channel configurations were used on alternate days: a static channel assignment, which is a current case for most Wi-Fi APs, and a dynamic channel assignment that used the COPE framework to reduce airtime usage on APs. The graph displayed shows the results of this experiment. The dynamic airtime scheme performed better for 10 out of 12 APs, and 4 out of 12 experienced between 20 and 45% reduction in airtime usage. Set Airtime Access is the AP under the COPE framework. It helps the COPE controller manage the AP's airtime access patterns. The controller divides the airtime into slots of 10 to 20 milliseconds each, and has the ability to enable and disable transmissions of the APs on a per-slot basis. The Set Airtime Access API uses 2 mechanisms to deal with the airtime access: throttle and slot. The table shows an example of the 2 mechanisms: a throttling transmission on the top and a slotting transmission on the bottom. The throttle limits the AP's transmissions to certain slots. This helps decrease airtime usage and reduce channel congestion due to nearby AP traffic. Slot is used to configure 2 APs to transmit in non-overlapping time slots. This becomes useful in decreasing hidden terminal interference that can result in package losses. The Set Airtime Access API includes 2 parameters: slot duration and transmit bitmap. The slot duration determines the time quality to use for airtime access management, while the transmit bitmap specifies the slot in which the AP is allowed to transmit. To kill the airtime access of an AP, COPE disables the AP's transmit queue to block packet transmissions for the required period of time. The figure shows 2 scenarios. The first one shows how the API provides a strict control over an AP's transmission and provides protection to important flows. Link 1 at 12 megabits per second degrades due to overlapping transmissions coming from link 2. After 30 seconds, the controller throttles link 2 by limiting its transmission to alternate 10 milliseconds time slot. This improves the performance of link 1 from 6 megabits per second to 12 megabits per second. In the second scenario, a link experienced poor throughput due to interference caused by a nearby hidden terminal. After 10 seconds, the controller detects this interference and protects the effective flow by configuring the 2 APs to transmit in alternating and non-overlapping time slots.
In conclusion, we have presented various problems that COPE tries to solve. We've also talked about the solutions to these problems. First, we presented a SDN framework for optimal configuration of densely populated residential access points. This solves the dense cluster of APs that do not talk to each other problem. Secondly, we have talked about the lack of user knowledge and how enabling better usage of the available spectra through centralized management allows better airtime usage and better data flow. Last, we talked about mitigating interference and protecting data flow using airtime access APIs. This allows mitigation of both Wi-Fi and non-Wi-Fi signals interfering with data flow of wireless access points, as well as various other Wi-Fi signal interferences. This has been Cope paper by Stephen and Talia, ECE540.
Thank you.
I'm going to cut that part out.